After having understood the light propagation in planar waveguides in the previous section, now in this section we will analyze light propagation in an optical fiber, the modes of light propagation in an optical fiber. So, if I look back to planar waveguide where the refractive index variation is only in one direction x and the propagation direction is z, then I had seen that the modes are given by these E and H. E is equal to E of x e to the power I omega t minus beta z, and H is equal to H of x e to the power I omega t minus beta z. You remember that these E and H are not constants. If they are constants, then they are plane waves, but here E is a function of x and H is a function of x. So, they are not plane waves propagating in z direction, but we had seen that these are the superposition of two plane waves, one going in plus xz direction and another going in minus xz direction, and that gives us a standing wave pattern in x direction which flows in z direction. So, they are the modes. If I look at rectangular channel waveguide, so now if I have confinement in x as well as in y, so refractive index variation in x and y both, so this is the kind of profile, then the modes would be given by E is equal to E of x y e to the power I omega t minus beta z, and H is equal to H of x y e to the power I omega t minus beta z. So, these E and H would now be the functions of x and y both. So, the confinement is in both the directions x and y, and those fields will propagate in z direction with certain propagation constant beta. If now I convert this into a cylindrical geometry, then it becomes an optical fiber waveguide. I can represent the refractive index profile in x and y, n square x and y, but because of cylindrical geometry it is much more easier to analyze the structure if I represent this refractive index profile in cylindrical coordinates. So, r phi. So, r phi are the transverse coordinates and z is the longitudinal along which the light is propagating. So, now what would be the modes of this kind of structure? Well, they can be given by E r phi e to the power I omega t minus beta z and H r phi e to the power I omega t minus beta z. So, this E which is a function of r and phi, so this particular function propagates in z direction with certain propagation constant beta. So, these are the modes. In all the three cases, what I observe is the direction of propagation z is common. So, I would like to make use of this, okay, to analyze optical fiber. Let me go back to the modes of the planar waveguide. So, I had TE modes with non-vanishing components EY, HX and HZ, and TM modes with non-vanishing components HY, EX and EZ, and these three equations relate these three non-vanishing components here, and these three equations relate the non-vanishing components of TM modes. So, what I had done actually, I found out EY and then I can get HX and HZ from these equations. So, once I know EY, I had formed the differential equation in EY, solved the equation for EY, got the modal fields. So, once I get EY, then from there I could get HX and HZ. Similarly, here I get HY first and then EX and EZ, and that is how I have the complete solution. But as I have seen in the previous slide that the common thing in all the three structure is the longitudinal direction z. Can I utilize this here? Well, if instead of solving for Ey and then getting Hx and Hz from here, I can also do another thing, that I first form the equation in Hz, solve it for Hz and then get Ey and Hx. Okay. Here what I notice is that the only longitudinal component here is Hz, okay, and Ez is 0. So, and in this case I can do the same thing, and here I notice that the only longitudinal component is Ez and Hz is 0. So, I can define my TE modes in such a way that the fields for which Ez is equal to 0, the fields for which Ez is equal to 0 are TE modes, and if I have Hz is equal to 0, then they are TM modes. Okay. If Ez is equal to 0, then they are TE modes, and if Hz is equal to 0, then they are TM modes. Now, let us look at an optical fiber. Okay. So, in optical fiber I have these E and H. Okay. If I substitute these solutions, if I substitute these into Maxwell's equations, del cross E is equal to minus mu naught del H over del T, and del cross H is equal to epsilon del E over del T, then of course I will get 6 equations. I will get 6 equations. The only thing is that I should now use cylindrical polar coordinate system r, phi and z and see what these 6 equations are. Okay. So, these 6 equations will give me the transverse components Er and E phi in terms of longitudinal components Ez and Hz. So, these are the 6 equations. These are the 6 equations which I get from those two Maxwell's equations. What I see here is that these mathematical equations from 1 to 6, these equations, if I do mathematical manipulation of these 6 equations, then they can lead to these 2 equations, one in Ez and one in Hz. So, I can form a differential equation in Ez or Hz, solve these equations and then get Er E phi, Hr H phi from these Ez and Hz, okay, using those 6 equations. However, what I see that if you look back to those 6 equations, let me look back to those 6 equations, I cannot find an instance where I can have only Ez or only Hz. That is, I am not able to find out where Ez is not equal to 0 and Hz is not equal to 0 at one time. I have that simultaneously both are non-zero, which means that now the polarizations are coupled. I cannot separate two orthogonal polarizations. Okay. So, two polarizations are coupled, and in general what I will get hybrid modes. I cannot get TE polarization and TM polarization in general, that I could be able to do in case of planar waveguide, that this is TE polarization and this is TM polarization, but here in general it is difficult. Okay. So, Ez is equal to Ez not equal to 0 and Hz not equal to 0 simultaneously are there. So, I cannot decouple two polarizations. However, there is one particular case where I can still have this decoupling, and this case is when there is no phi dependence in the solutions. When there is no phi dependence in the solution, then let us see what happens. So, if there is no phi dependence, then I put these del phi terms 0 everywhere. Okay. So, these del phi terms are not there, then I can see that in these three equations I have only Ez, 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 okay, and there is no Hz. So, in these three equations, if I consider these three equations, then Hz is equal to 0, and in these three equations there is no Ez. So, Ez is equal to 0. So, only for this case I can separate out the two polarizations. I can decouple two polarizations TE and TM. So, now for phi independent solutions we can have two cases. One is Ez is equal to 0 and Hz is not equal to 0, which is nothing but the case of TE modes, and another is when Ez is not equal to 0 and Hz is equal to 0, which is nothing but the case of TM modes. So, in this way I can separate out two polarizations, but in general what I will have Ez not equal to 0 and Hz not equal to 0 simultaneously. So, Ez not equal to 0, Hz not equal to 0 simultaneously, it means in these kind of modes two polarizations will be there, and they are called hybrid modes. They are hybrid modes. In these hybrid modes there can be two instances. One is when Hz makes larger contribution than Ez, then we label them as He modes, and when Ez component makes larger contribution than Hz, then we label them as Eh modes. So, in fiber I can have TE modes, TM modes, HE modes, EH modes, okay, and these modes are also known as vector modes of the fiber. Here I have plotted some typical vector modes of the fiber and their electric fields. So, this is a typical TE01 mode, this is TM01 mode, this is HE11 mode, this is HE21 mode. But the fiber that we practically use has a small index contrast. The index contrast between the core and the cladding, the relative index difference between the core and the cladding is typically 0.3%. So, which is very small, and if you look back, if you look back to the analysis of your symmetric planar waveguide or even asymmetric planar waveguide, we see that if the index contrast between the high and low index regions is small, then the propagation constants of TE and TM polarizations they merge. Okay. It is very difficult to distinguish between TE and TM polarizations in terms of their propagation constants if index contrast is small. So, here we use that fact that if index contrast is small, then the fiber will not distinguish between this polarization and this polarization. So, in such kind of fibers we can still have the modes which are linearly polarized, that is, if one is polarized like this, then another has to be like this, or if there is any arbitrary polarization, then that arbitrary polarization can always be represented as the superposition of this and this two orthogonal polarizations, horizontal and vertical. So, in case of weakly guiding fiber, what we have are linearly polarized modes, and we can have two orthogonal polarizations which have nearly the same propagation constants. And now if I say that psi is the transverse component of electric field. So, you have a fiber and psi is the transverse component of the electric field, then it satisfies the equation del square psi is equal to epsilon naught n square mu naught del 2 psi over del t square. This psi is capital psi. So, it is a function of all the spatial coordinates as well as time. In general, this n square is a function of r and phi, and if this is a function of r and phi, then I can in general write this capital psi, which is a function of r, phi, z and t as psi small psi of r phi e to the power I omega t minus beta z, because n square is not a function of z. So, z part can be separated out, and this is how the solution of z part and t part will come out. We have seen this several times. So, now we want to find out this psi r phi, this function and see how does this propagate. This function psi r phi represents the mode, this function psi r phi represents the mode which travels with propagation constant beta. So, the problem reduces to find out this now. So, for that what I do, I put this capital psi back into this wave equation, and when I do this, then this equation becomes this del 2 psi over del r square plus 1 over r del psi over del r plus 1 over r square del 2 psi over del phi square plus k naught square n square of r or r phi minus beta square psi is equal to 0. In this course we will limit our discussion only to refractive index profiles which do not depend upon phi. So, we will consider only n square of r and not n square of r phi. So, now this is the equation, and if n square is a function of r only, then this solution psi r phi can be separated out in r and phi. Okay. I can separate out r part and I can separate out phi part, and of the psi r phi, as I have said earlier, that they are now the scalar modes or linearly polarized modes. So, since n square is a function of r only, not of phi, so psi r phi can be written as r of r and capital phi of phi. And if I now put this back into this equation, then I can separate out r part from phi part. So, I get r square over capital R d 2 r over dr square plus small r over capital R d capital R over d small r plus r square k naught square n square r minus beta square is equal to minus 1 over phi d 2 phi over d phi square. So, I have separated them out. The usual procedure now is to equate it to some constant, and since this is second order equation, so I will take the constant in the form of square. So, I take it as L square. So, first let me solve this phi part, and the phi solution comes out to be cosine L phi and sine L phi. I make the use of the fact that in phi direction the solutions are periodic. So, you start at some phi and then you make a round of 2 pi, you come back to the same point. So, capital phi at phi plus 2 pi is same as phi at phi, okay. So, that there is there is only single solution, then this restricts the values of L to only integer values. So, L can only be 0, 1, 2 and so on. So, this is the phi solution. Now for each values, and we see that in phi direction now the solutions are discrete. The solutions are discrete because of this condition. So not all the values of L are allowed, only certain discrete values of L are allowed, which are integer values. Now for each of these integer values of L, I can find out the solutions R. Okay. So let me now look at R part. So the R equation is R square d2R over dr square plus R dr over dr plus k naught square n square of R minus beta square times R square minus L square times R is equal to 0. So this is the R equation, and I can solve this R equation for a given n square of R. What is the n square of R? I am going to take in this course. I will again limit myself to step index fiber, and that to only 2 layer fiber. So which has only 2 regions. So n R is equal to n 1 when R is less than A, and it is n 2 when R is greater than A. So this is the core, this is the cladding. Core has refractive index n 1 and radius A, okay, and this is infinitely extended cladding. Okay, so this is the R equation and this is n of R. The procedure to solve this equation is exactly the same as we have been doing for planar waveguides. What we will have to do? I will have to write this equation in this region, in the core and in the cladding. So in the core, which is defined by the region R less than A, this equation becomes this, and for R greater than A, which is the cladding region, the equation becomes this. We should pay attention again that for guided modes, for guided modes, our beta over k naught should lie between n 2 and n 1. So beta lies between k naught n 2 and k naught n 1. So that is how I have arranged the terms here in order to have this quantity positive, in order to have this quantity positive. So I have plus sign here and k naught square n 1 square minus beta square, and a negative sign here and beta square minus k naught square n 2 square here. So now I have these two equations which I have to solve to find out the values of beta for any given value of L. L can be 0, 1, 2, 3 and so on. Okay. So let me define this k naught square n 1 square minus beta square as some u square over a square, and this as some w square over a square. So these equations now become r square d2r over dr square plus r dr over dr plus u square r square over a square minus l square times r is equal to 0 in the core, and in the cladding r square d2r over dr square plus r dr over dr minus w square r square over a square plus l square times r is equal to 0. So now I have these two equations, I have to solve them. If I have a little background of mathematical physics, then I can immediately see that these are Bessel's equations and the solutions of these equations are Bessel functions. Okay. So, so where u square is this and w square this. So I am going to get the solutions of these, but before that I observe the fact that if I do u square plus w square, then it becomes k naught square a square times n 1 square minus n 2 square, and by this time I am able to recognize this kind of term very well. This is nothing but the normalized frequency V. So, this is V square. So, in case of optical fiber, I have V is equal to 2 pi over lambda naught times A is the radius, which is half the diameter, times N1 square minus N2 square root. This is normalized frequency, and again it contains all the fiber parameters and the wavelength. Let us come back to the solutions of this. The solution of this equation is given by JLUR over A in terms of JLUR over A and YLUR over A, which are Bessel functions. And of this equation, KLWR over A and ILWR over A, which are modified Bessel functions. Okay. So, if you go back to your planar waveguides, I had in the region mod x less than d by 2, where nx was n1, I had the solutions cosine kappa x and sine kappa x, and in the region mod x greater than d by 2, where nx was n2 and of course n1 was greater than n2, I had solutions in the form e to the power minus gamma x and e to the power plus gamma x. Okay. So, I had oscillatory solutions in mod x less than d by 2 and exponentially amplifying decaying solutions in this. Here instead of sine cosine, I have some JLYL. Instead of e to the power minus gamma x and e to the power plus gamma x, I have some KLIL. Okay. So, what these solutions are, what these functions are, and how do I understand them, and then how do I proceed further, I will see in the next lecture. Thank you.